I was asked by Ivan to actually give an overview of different optical and photonic things related to crystals. When I started to look at that, it looks like so broad, I feel that really nobody can do justice to it. So I decided to really focus on a couple of things. One of the reasons for doing that was in this workshop, you'll see there are experts in everything. So really giving overview when they're going to talk about the detail and with much more knowledge wasn't going to be the right thing to do. So I'm going to talk about a number of different systems, but before starting to do that, since I work with NSF, I have to put this disclaimer. So if I want to say anything about against or for evolution, nobody's going to blame NSF. It'll be my fault. Okay, so what I'm going to talk about is two different types of systems, photonics, and these include a couple of examples from nature, living photonic systems, and some that in hindsight, I realize that we actually have made, and can perhaps be a more complicated version of those can be made in the future. And the second part has to do with the role of liquid crystal that's now beginning to be recognized that it can play in organic photovoltaic materials. So first, the living photonic systems, and in fact I want to start with something you saw yesterday in Steve Jacobs' talk yesterday. He showed it very quickly that beetles have this reflective, brilliant green color. And it turns out it's actually polarized. It's left circularly polarized, and if you look through right circular polarized, you really don't see the colors. It turns out that the polarization is, in fact, these colors and polarization play a role in attracting mates for these insects. So if you see equally bright color but no polarization, it doesn't work. If you were to focus on one of these surfaces that are looking green, with a microscope you'll find that there are structures, more like cellular structure, and the cells are made of either pentagon, hexagon, heptagons. If it is flat, you see more hexagons, as you can expect. And if it is curved, you see more pentagons and heptagons. And in the middle, there's a bright spot. So one question comes up, okay, what is giving rise to this color and circular polarization of the reflected light? I happen to get a recent results which have been submitted for publication by one of our collaborators at Georgia Tech, and he has done confocal microscopic study of one of these rings. Finds that these cells actually have texture, and in fact the structure looks like a cone. Base is wider than top, and these resemble, in fact, illustrate fingerprint texture. So really, the structure we're looking at has a lot to do with liquid crystal. This is coloristic structure in each cell, and of course you expect then polarized light reflection from coloristic structures. So that's one simple result. Second one is on butterflies, particularly the morpho butterfly that has brilliant blue color. And I was reading papers, they say that in fact this is so brilliant that when you fly over there in habitat in South America, you can see reflections from the plane flying about 5-6 miles high. It's a really impressive structure that nature has formed. Again, the question is, what is giving rise to these field reflections? And a number of studies really have been done. In the literature you can find, these are some of our microscope pictures, so they started to look at the rings. Under optical microscope, you will see really blue scales, or tiles, more like blue from a house. They are covering portions of the other tile next to them. You can magnify and rotate and find out that in fact light that's reflected is polarized. You can go a little bit more in detail, and in fact look at the structure of the ring. It has three different parts. One is the top surface that we're looking at, blue color, and in this orientation looks sort of dull brown. But behind these scales, if you break these away, you'll find some supporting structure behind it, which is grayish. And then below both of these, you find a sort of base structure that has ridges, and these bright spots you see are actually more like cuticles supporting or holding these flat rectangular scales in them. So we have really intricate structure, and we can really go into details of different parts of it and span hours. In fact, different species of the same butterfly family, not being a biologist, so we use the word family here, have variations of these structures. But I'm going to look at only the top part, just to show you that there's actually a role being played by liquid crystalline-like structures in nature. If you look at one of these scales, in SEM, we need to see there is finite structure. These are, by the way, the cuticles that hold these flaps onto the the base. And these lines can be magnified. More you magnify, the more details you get. Eventually you begin to see that these lines are made of even finer structure, and there seems to be a wall on which you have these ledges coming out, and the wall itself has holes in it. You can go a little bit more in magnification and find out that in fact these are the structures we're looking at. These are the ridges in the center is the wall that goes down. So if you were to look at a cross section of this part, it looks like a tree. You have a supporting structure in the middle and the ledges on both sides. And of course you can expect that light coming here is going to be reflected, and you have essentially a very effective diffraction gradient. So that's why the brilliant color comes. The spacing here, if you scan it with AFM, again starting with the low scale, you can go finer and more resolution. This is one of those scales that is being scanned by AFM, and then take a cross section from this line. You can see that, in fact, since AFM looks at the height variations, we are going from one ledge to the higher edge, which is shorter, and then down on the other side. And this is how the height profile looks. So we're looking at structure dimensions of about 990 nanometers versus 4.5 width, and the step size is about 190 to 195 nanometers. Again, basically reflections will come from different parts, and interference gives rise to the brilliant reflections you see. Now, as you diffract from a gradient-like structure like this, we expect some partial polarization, but the polarization is really much more effective than you will expect from a gradient. So the question is there something else that gives rise to perhaps a polarization? So we try to see, really not hoping anything, we're going to see an X-ray diffraction. And X-rays are really sensitive not to these length scales, but much smaller, multiple length scales. So we did X-ray diffraction in one of our runs at Argonne from one wing and got a surprising result. This is, I'll show you some more pictures of the same thing. You can see a number of reflections here, but many of them, others, are buried because we don't have the right color contrast. You can rearrange that and sort of doctor the picture to reveal all different reflections, and see that there is a set of reflections going this direction, another one this way, and diagonally, and black and white shows a little more details. But if you were to draw a schematic, you can see under different contrast conditions here, this is what the pattern looks like. So we have about 7 to 8 very nicely formed, very well oriented peaks in X-ray diffraction. And actually something is amusing here, that if you think of this as the wing, on both sides, this resembles butterfly. So one can say that since X-ray diffraction gives you the Fourier transform, the Fourier transform butterfly is a butterfly. But the other things that come out from this pattern is obviously it's not isotropic. We are looking at different structures in one direction than the other. And an isotropic structure is what we see in crystals all the time. The other part is that some of these are sharp. This is sort of linear reflection, very narrow, very broad. So looking at different, if we have an order corresponding to this peak, it goes to a certain length scale, because the width is mostly proportional to the domain over which the structure extends. So we're looking at sort of short domains versus longer term, more distance domains. So looking at structures again, very similar to what we see in liquid crystals. Now, we haven't completely finished analyzing that, so I can't tell you what the structure is, but this is obviously made of chitin, which is the material making organic sacs, shells, and wings. And the structure of chitin can change depending on what else is in it. So we're going to analyze this. In fact, I'm going back to Argonne this afternoon to continue some of this work on butterfly and beetle wings. The next part I want to talk about, when I was looking for what photonic things I can talk about, I went to Wikipedia and came across this picture, which reminded me that we had actually done a few years ago some simple things. Here, basically looking at periodic structure in one dimension, in 2 different dimensions, and periodic structure of volumes that have different index of refraction, or you can make 3-dimensional reflections. So turns out we actually have made a structure of these 2 types by using a very simple process, and that's phase separation of liquid crystal from a polymer. We have photosensitive polymer in which you can dissolve the liquid crystal, pneumatic or ferroelectric, SMRTC, or anything else you want. And then expose, this is the cell I'm showing here, it's filled with mixture of 3 polymer and liquid crystal, then you can shine UV on it to initiate the polymerization process, and we can choose the mask that looks like a linear grating. So the exposure is only selective in certain areas. So UV comes through the mask, exposes this part, and when the polymerization starts, we have intensity very low, so it's a very slow process. Main fact is that the polymer begins to hide under the shadows. So that's one way to understand what happens as a result of phase separation. So the polymer molecules migrate to the darker areas. So we have essentially 100%, this other way around. We get 100% polymer in these portions, and then liquid crystal and polymer, which then phase separates into two parts. So we are looking at a periodic structure, liquid crystal volume and polymer liquid crystal, and it's basically a reflective index variation, and it's going to act like a grating, which it does. So you can actually shine light through it and make different pitch gratings with this process very easily. And since this is pneumatic and oriented on the surface, we have coated that with rough polyimide. We can apply field and control whether it reflects or not by adjusting the contrast between the polymer and the liquid crystal next to it. Now we can use the same method by using two linear masks by crossing them and get a two-dimensional phase separation where you have areas that are basically polymer, isotropic all the time, and the bright areas of liquid crystal. In this case, we're using ferroelectric liquid crystal, so you can change to either positive voltage or negative. When you get full negative, there is no contrast left. So under -10 volts for this cell, you get practically no diffraction. As you remove the field, you can begin to see diffraction. With positive 10, you get very good diffraction right in front. So looking at really very simple liquid crystal polymer composite structures that can be linear or two-dimensional diffraction graded. We haven't really gone to the third dimension yet, and I think some of the experts today will talk about perhaps in a different system, three-dimensional photonic crystals. One other variation on the technique that I showed you is that instead of gratings, if you were to use circular dots in your mask to cover some areas from exposure to UV, what you get is actually a nice array of circles. This work was done by James Kim, who was postdoc in our group. He's a professor in Korea. And in fact, this was done at a time when it didn't have a mask. So he actually printed circles in a transparency using inkjet printer and used those as a mask. What we're looking at really is the structure, which is shown here in terms of dimensions of one of these circles, and the height profile of polymer. You can watch them with a scan. Looks like it's formed by diffraction from circular cross-section, circular aperture. And of course, these areas are filled with liquid crystal. So you're looking at a plano convex volume in the middle that's filled with liquid crystal. It's aligned because the surface that it's in contact with has been prepared properly. And then you have the secondary maxima that are also filled with liquid crystal. So not only we have a central part, which is plano convex, and it's going to focus any light that comes to it, so it's going to act like a micro lens. But you can also perhaps exploit the secondary structure to get Fresnel lens from this process. Now the good part is here, for this particular example, we had focal length of 1 centimeter. You can change the thickness in the process. We're able to get focal length of 1.2 millimeters. And then by applying field, you can go essentially infinity. You can adjust the index of refraction between polymer and the crystal to go from focusing lens to defocusing lens by just applying the field. So there's quite a bit of freedom here to play with these structures. 3D we haven't done, and I think we can probably hear from people, experts here. But that should also be possible to make this process all you have to do is expose holographically to a intensity variation that's three-dimensional, or use a raster laser beam that focuses at different depths. Okay. Now, the second part I wanted to talk about the role, how basically liquid crystals understanding and knowledge of those can be applied for photovoltaic materials. Now, photovoltaics, as we understand, is the conventional ones are made of semiconductors. Silicon is typical material, and the process is that you have a p-doped and n-doped semiconductors in contact with each other. There is junction there, and the diffusion of holes and electrons creates a small voltage drop across the junction. So when you shine light, it can excite. It can create pairs of electrons and holes, and the field there basically pulls them apart in opposing directions, and you can create a current in the external circuit. So So for semiconductors, that works nicely. But for organic semiconductors or other materials, there is no internal or intrinsic potential difference to separate the charges. So when you shine light, basically you have a pair of electron and hole drifting around for a short time, and they can recombine unless you are ready to collect it. So one of the problems is having enough percentage of these excitons or charged electron and hole pairs to be collected without keep them from recombining. Now this has a lot more details than we need to focus on. This is a cell that was made by Brexel, and he is using dye to actually enhance this charge production. Basically a titanium oxide next to a layer of dye, and when light comes in, it creates electron, which can go into titanium oxide and leaves a positive charge, which is actually gold, which goes through this mediator redox processes, and you can actually have electron flow through the circuit, so you can generate electricity using this simple process. The problem is that if you're able to collect all the electrons, this is great, you'll have highly efficient organic solar cells. But there's a competing process, and that is that the electron spends enough time in titanium oxide that can combine. So it doesn't really go and basically finds a hole, positive charge, and that's the end of it. And in fact, very high percentage of the electrons don't get collected. So how can you enhance that? That's one issue. The other is you can separate the charges. How do you collect them very efficiently? So people have been doing different methods. One of them is just to mix P and N-type organic semiconductors, polymers or otherwise, and make a sort of a material that has many interfaces. And at the interface is where the charge production takes place, and then you have to find a way to collect the charges by perhaps doping the material with CNT or other than particles. So basically it boils down to how efficiently can you collect the charges and then drain them from the bulk of the cell to use them for an external circuit. Now one method that seems like it's plausible is to make use of the complex of a dye molecule and cyclohexane. And I apologize for that. These are actually cylindrical oligosaccharides made of 6 or 8 sugar molecules. And the shape of this complex looks like, or cyclohexane, looks like a thimble. It's sort of cross-section of a cylinder or a cone that has different dimensions on one side and the other. And it was reported in 1981 by Suzuki and Sasaki that if you put a dye or a polymer in these cyclohexanes, by the way, these have been used by pharmaceutical industries for a long time to make drug formulations. And the idea is that inside you have hydrophobic environment, outside is hydrophilic, so you can actually put organic hydrophilic agents inside to deliver in human body different places. Being sure that it's safe. So anyway, when you mix orange dye and cyclohexane, one sees this, between cross-polarites, one sees this color, which obviously tells you that we're looking at anisotropic structures. By itself, cyclohexane doesn't depolarize light or dye. I don't think it does, but mixture does. And analyses have shown that these two entities exist not independently in the mixture, but something else. So they form a complex. And the explanation is that what happens is when you put cyclohexane in contact with polymer or dye, the polymer goes inside cyclohexane. If these are short molecules, they can associate with each other and form a linear structure more like a necklace, fairly long. And of course, these are linear, they can form anisotropic phases. And the added advantage of forming a structure like that is that you may have good conduction either on the inside surface or inside surface to collect charges. There is dye here, which is going to damage electrons in holes or create excitation. And being really very short distance to go out, typically the distance that electrons travel in organic semiconductors is 10 nanometers. So if they can go out of that, it's hard to find the hole to come back and recombine with. So these may be more efficient in separating the electrons and holes, and the connecting properties may be very helpful in collecting the charges and provide good conduction path for these charges. They also add to the chemical and photochemical stability and the water soluble. Many good things that you want in these days from systems that can be used in public. So these have advantages obviously in solar cells. organic LEDs or other organic conductors. Now, we have seen some of these results where you see anisotropic scattering, or at least indication that they have anisotropic structures, which most likely are crystalline. We did actually scattering from a mixture which was very dilute of orange 2 and CD, cyclodextrin, which was gamma CD, 0.07 mole percent. So it's really very clear, easily flowing liquid. And when we shine X-rays at 89 degrees, it's isotropic. So we really see 3 diffuse rings, signature of the liquid phase. If you cool it down, like below 80 degrees, there's no sharp energy. You can see things changing. At 44, we took this diffraction pattern. And what it shows is that in one direction, remember these rings are not really complete rings, but they are showing preferential orientation of something in the sample, that these are essentially diffraction is arising in this direction. So whatever is giving rise to diffraction is confined to a plane, and then we have a small angle, very diffuse diffraction patterns, which are similar to the pneumatic phase, a little bit sharper than pneumatic. And the length scale of these reflections corresponds to 6670 angstroms. And there's nothing, either in cyclodextrin or dye, that is that big. It's about 10, 12 angstroms. So we're looking at, obviously, composite structures which are elongated, long, and a qualitative explanation of what we're looking at, which obviously is not rigorous and may have to be modified, is that at high temperature, we're looking at these cyclodextrins with dye molecule inside, floating and moving around a bend, so more like an isotropic phase of these entities, which is not a molecule anymore. And then as you go to lower temperature, they form strings, as was emphasized earlier, to explain the birefringence. And the length of these could be 10 units or so. But if you look in the other direction, these cyclodextrin can touch and pack nicely to form a plane, or at least a two-dimensional structure that resembles crystalline phase. So we're looking at crystalline order and perhaps not crystalline, but somewhat like crystalline order in this direction at a large landscape. Okay, now assuming you can make these, and the picture we have is right, it seems to be the case, then you can think of making photovoltaic devices using a number of different techniques. These are just, at this point, concepts, how we can do it. By self-assembly, put dye and cyclodextrins together, you treat a surface and create homeotropic orientation of these complexes. So we then have really nicely aligned cell, which has dye in it, and a way the cyclodextrins conduct out the insulator. As soon as the charges come out, they can't go back into that easily, but then the surface can provide a conduction path to the electrodes. So these could be fairly efficient photovoltaic devices. You can also make highlighted cyclodextrins and then use low nanoparticles in the solution and on the substrate to get a structure very similar to that. That could be another possibility. There are other numerous possibilities one can think of, but it shows a way to perhaps improve on the efficiency of organic photovoltaics. The second system, which does something similar, was basically this molecule, or its homologs, synthesized by Quan Li at Kent State. These are porphyrin derivatives, which are naturally disparate chlorophyll. So they're very efficient in harvesting energy or visible part of the spectrum. And the idea is that if these can be used in an efficient way in architecture that we understand and control, then perhaps these can be used even more easily and more efficiently as solar energy harvesting devices. So we have basically studied some of these compounds, and the one we have shown here, carbon 12 and 14, they show this phase sequence. Isotropic phase at high temperature, then we have hexagonal columnar phase, and then another columnar phase at lower temperature before it becomes a crystalline phase. In fact, what we're looking at here is the texture that you see from columnar phase. We have dark area and some that are different colors. To find out what the structure is in different parts, we did microfocus X-ray diffraction with non-convex at our dimensional lab. And what we find is that, in fact, depending upon the domain you're looking at, here we're looking at a domain that's dark or homeotropic. So looking along the axis of the columns, and you see hexagonal pattern, which you sort of expected if it was column phase. If you're looking at somewhat brighter, where the hexagons are tilted, you can get 2 or 4 reflections. So basically, these show us we're looking at something that's hexagonally structured but oriented differently in the sample. The goal is, if you want to get polytropic orientations, to get all of them in this configuration. And of course, this domain has it. You can change temperature, you can see coexistence of one covalent phase and the second one. You can see two spots, and eventually you're left with only one set. So this is basically looking at transition from one hexagonal phase to the other. But from the sharpness of these peaks, how well defined they are, it tells me that the orientation, which is homotropic, is preserved as you go through the transition. And in fact, you can go to the crystalline phase, it's still preserving the orientation. Now, based on the crystals, my group mates actually are fairly good in orienting these complex materials. So, Chin-Woo Kang was able to make cells that were several centimeters and it's completely homotropic, there's homotropic. So we have a structure of these orphan molecules, which looks like a polymer phase with hexagonal symmetry. And of course, they're photosensitive, so you can actually use them for solar energy harvesting. One can also dope these with carbon nanotubes, which are shown in orange and black. And there are papers that show, in fact, that if you put CNTs in polymer phase, they go in between the cylindrical units. So if you have this architecture, you actually have very highly conducting path in this direction and sort of poorly conducting path in this direction. So these could be, again, very useful for solar energy harvesting. So basically what I show you is that there are systems beyond just display applications of liquid crystals where our knowledge and experience can be used to make, obviously, more efficient photonic structures and photovoltaic materials and devices. Now, before I go to questions and answers, I want to make this little announcement. In October, we have an international symposium in Kent, and it's on biaxial magnetic phase, which was discovered in 2003. I believe it was in Kent. Now, biaxial magnetic phase has two directors. So you have one of the dimensions of the molecules, so they're bent core, it's formed in bent core. But theoretically, you can also think of objects that are rectangular in shape. So you can align the long axis that defines one of your directors, and another short axis that will be your second director. So hence the biaxial phase. And there are a number of papers, people that have been active in this area, and I think it would be very good to sit together and talk about what the questions that we need to be addressed are in this field. Where should we go? Who should make what measurements? Establish some collaborations. So all of you are welcome to this symposium. It's 2 days long. We're trying to find funding, and the goal is to have a registration fee, just like here, and provide at least partial support for speakers and young researchers. Okay, with that, I'll stop.
Thanks. We have a couple minutes for questions.
About the orphan columnar physics, but that one is only P channel, right? It's a P channel. But if you want to do the transfer, you need an N channel too.
Yeah, but those are the problems to have. First is to have materials that are useful, and I think we have a family of compounds that we use.
Yeah, I mean, if you want to use for photovoltaics, you need a two part. You need a N channel, P channel together.
Right, well, some of the electrodes act as P. I think indium and gold are used very often. So one is electron accepting, the other is not.
Like fluorine or?
Not fluorine, basically, what is the word here? Their work function difference can help.
I had a question about that because I had a question which actually goes back to your very first slide. I'm just wondering, how many biological systems do you know of where the organism has gained some sort of evolutionary advantage from being sensitive to polarized light? Are there any? Is it really proven for the case of the beetle that circular polarization is important?
For refining mix, yeah. I mean, I basically
aware of any other cases?
I think butterflies do that. There are a number of insects and animals that have these coatings in different forms. Some are linear, just air that are reflected. And in many instances you find that in fact polarization and the brilliance how to get affected the meats.
I had a question about the cyclodextrin inclusion complex. I would guess you could see some solvatochromatic effect of including the dye that would disfavor the charge transfer state, say relative to Dressel cell, which is, sort of polar view. Did you see any of that, or?
We haven't really gone to that extent yet. We're just deciphering the structure of what is it and how can we understand, how much can we understand about it. And I think your question is more for chemists. I'm not sure I can answer that. Save it correctly.
If not, we'll skip the next one. So we'll move on to our next presentation by Satyendra, entitled Adaptive Photonic Crystals.
We turn up the house lights just a little bit. The house